Hello. Hi.
Yes, sir.
Hello, good morning, sir.
Good morning. Yeah. So before I start today's lecture, I would like to say a few things. First of all, mm, officially today is the last lecture, but your exams are on 1st of January, right? So it is still kind of how much around 15 days away. So what I mean, so first of all, I was thinking uh, of taking some extra classes, maybe on even this Saturday or even some other days, all to kind of sort out your doubts, questions, and so on. Okay, so please, I mean, if you can come up with a consensus about how often do you want your classes or discussions, that will be good. Okay, so it is nothing new will be told, nothing new will be discussed, all about problem solving and clearing of doubts. Okay, I'll be happy to take more and more classes, or if the TAs are, if you want some particular TA to talk to you, perfectly fine. Okay, so from now on till the exam, uh, please, I mean, let us know, should we have classes as regularly as we are having, or should we have this once a week or something? Okay, I leave it to you completely. I know this week is the official end of this course in terms of the classes. After that, there is preparatory week, but you guys can ask me at any point of time that, okay, can we have a problem solving session on something? Again, it is all, nothing is compulsory. So if you guys want, you can attend. If you don't want, you don't need to attend, but you have to let me know. Okay, so maybe I need someone to kind of take the responsibility of telling me. So I mean, maybe Anvit Garg, I mean, since you are one of the persons who uh, uh, have been kind of one of the representatives of the class, can I bank on you to tell me this information?
Yes, sir, I'll tell you.
Okay, okay, good. So so that is one thing. Second thing is that I have still not been able to finish the correcting of exercises. I will certainly do it in the next 1 or 2 days, and I will let you know. And again, see, problem is that I realize that while correcting exercises in classroom format, it's a bit hard for me to give comments inside this inside the notes and all. I mean, I can give marks about correctness and all, but not about the comments. So I will still try to see if I have some particular comments to make or something. I'm trying to add some of them, but what you will get to see is basically your scores. Basically, that's all. And if you have any doubts or something like that, of course you can ask us. Okay, I kind of will try to um, get these corrections done in a couple of days. I mean, I'm in the process of doing it. Okay, so that is the second thing. The third thing is that okay, I want to repeat this thing that I have told earlier. Okay, the 1st of January is your exam. The exam has 8 problems, uh, 15 marks each. Okay, now they are not, at least not all of them are hard. Maybe a couple of them are hard or something, but all of them are pretty much doable. And so if you are comfortable with whatever is being done now, whatever has been worked out, you have worked out the problem sets, assignments, some more problems here and there, you should be, I mean, getting something like a 90% or 80%, like a cakewalk. Rest of it is there. But I should say again, this is something I requested you earlier also. Write every question on a different paper. Okay, meaning problem 2 should start from a new page. Okay, you will be clicking photos or scanning it or something and sending it to us. So every problem should have a new paper. It should not be that first, how, I mean, the end of problem 1 and then problem 2 start somewhere in the middle. That should not happen. Okay, problem 1, is in a separate collection of sheets. Problem 2 is in a different collection of sheets. Okay. On top of every sheet, okay, write your name, please. So in case something weird happens, I will be able to understand what's going on. And the third important thing, this is something very important, write the number of the problem very carefully, very clearly rather, what you are trying to solve. Okay. And in the bottom of the page, write down the number of the page. So say one option is that if you are solving problem 2 and you are in the third page for the problem 2, you write say problem 2 dash third page or something like that, or 2 dash 3, something like that, right? So that in case after when you are clicking the photos or uploading it and all those things, something mishap happens, and I mean there's a mixing of the pages and all, I still will be able to decipher the whole thing. Okay, this is, I mean, that's very simple set of instructions. It's all written on top of the paper. Okay, so that is something that you should not, I mean, you should know it, but this is exactly what is written. In fact, I can possibly share you, I will share you all the instructions that are there in the beginning of the paper, I mean upfront. This is what you are expected to do. The time for this class has been set for 2.5 hours, and then I think there is 45 minutes for uploading your stuffs and all. So basically it is 3 hours 15 minutes or something like that is the time. I am not such a I'm not very strict in times. So if somebody says that, okay, can I take another half an hour or 1 hour or something like that, I would not mind. Okay, I will not mind. The thing is that the last thing is that, I mean, it is at this point with this kind of everything being conducted in a virtual way, it is an honor code. It is impossible for me or anybody to kind of verify whether you guys are cheating or not cheating. I mean, see, again, it is open book. So you are open book, open internet. So there's nothing much we can do about it. We know that. But what we don't want you to do is that talk to each other, get help from somebody else. Okay. I mean, you don't have a senior or someone sitting there and trying to solve it to you and give it to you. That is something, I mean, again, nothing but we cannot, I mean, if you do it, I don't think we have the mechanism to catch it or stop it, but it's an honor code that we kind of hope that this kind of, I mean, you guys will be honest about it. Okay. Usually I am not, I mean, I give good marks, so grades is not a problem as such. It should not be a big trouble if you have done the assignments and this stuff. It should kind of be pretty simple. Okay. Okay. Now there is, yeah. So there is one more thing. I have decided to make a Google form and it will send it to you guys. Okay. Now in Google form, anyone can fill in anything. Okay. It will be more for a feedback of this course. So if you guys already have a feedback and you have managed to coagulate it and send it to me, that's outstanding. I would love that. Okay. But if not, I will just send out a Google form and you guys can fill it up. You can fill it up through an incognito window, so that nowhere I will be able to know also who has filled it up. Okay, so so it will be completely be. I mean, if you believe in Google, then it is then it will be secured and private. Okay, so I will have no idea who has filled up what. So you should without any fear give this the review for this course on suggestions and so on and so forth. Okay. Yeah, I think technically, I mean, in terms of the logistic things, that's all that I have. I don't think I have anything else. So, okay, good. So I have some things that I want to talk about today, particularly in this related to this last section that we were working on, which is like P, NP, deductions and so on. But before I go into that, let me ask you, do you have any questions? problems that you want to discuss or something, so on and so forth?
Sir,
Yeah.
Sir,
Yeah, tell me.
sir, can you please explain? Sir, can you please explain the click problem and the set cover problem? I mean, the connection between them.
The connection between them. Okay, so okay, so maybe this is one thing. Okay, so okay, so let me say this one. Okay, so see, I don't know exactly the I mean, I don't know in the top of my head this reduction, but say you have the set cover and you have the click, right? So what is the set cover? The set cover is, okay, set cover, right? Meaning you have been given a collection of sets S1 to Sk, all of them are subsets of say 1 to n. I mean, no, this is not the right thing. So each of the SIs are subsets of 1 to n, right? And you want to pick the minimum set T subset of S such that for all I, T intersection Si is not equal to empty. This is the set cover problem, right? I mean, there are so many formulations of the set problems, I always get confused. This is the set cover problem, right? Can somebody confirm?
Sir, what is S?
Sorry, no, what is S? Not S. I mean, maybe I should write it here. Sorry. This Si is equals to omega, so this is omega. This is the set cover problem, right? I think so. Okay. I mean, so if not this one, there's some other version of this one, but all of them are basically the same thing. I mean, okay. Now, what is the click problem? You have been given a graph G, all right, and you want to find the maximum W subset of V such that for all UV in W, UV is in the H set. Right. So now, okay, see, both of them are written in terms of the optimization problem. So none of them are decision problems, by the way, at this point. Okay. Now, if I have to convert it to decision problems, what would it be? So one thing is that this is the usual decision problem. Does not okay? Is there a set cover of size less than or equal to say R? Okay, where R is some parameter, and this one is that is sorry.
The version of set cover problem that we know asks us to find the minimum number of subsets Si whose union is the full omega.
Okay, good. So that is the another version. Okay, so this set cover, whatever I wrote, is basically kind of the generalization of the vortex cover problem. So you are saying that the other one. Okay, fine. So you want to find the minimum T subset of 1 to K such that union of I in T Si equals to sigma omega, right?
Yes, sir.
Yeah. And the question is there a set cover of size less than R? Okay. And now this and the corresponding click problem is there a click of size greater than equal to say C? Okay. Now, okay. So first of all, both of these problems are NP problems. Okay, that's one thing. And it turns out that both of them are NP hard, but forget that, or NP complete. Okay, but what I want is something else. Okay, so you guys wanted to relation between these two. So what you can prove is this following thing. What you can prove is that set cover is easier than, okay, click, and you can also prove that click is easier than set cover. So what does it mean? Okay, so if I give you an instance, so if I, or say, so what is the instance of this one? If say S1 to Sk is an instance of set cover, okay, you can take this one, do some kind of a construction, produce a G. So let's call this one S. Okay, this G is of course something that you construct out of S, okay, such that, okay, S has a set cover of size less than or equal to R if uh, if and only if, okay, uh, yeah, if and only if GS has a clique of size more than or equal to, let's say this one as C. Okay, now this C, but this C is something, okay, so maybe we should not write here. So more than or equal to C, which is basically a function of a few things. What is the function of? It can be a function of the sets S. It can also be a function of this R. Okay, so this is what you can prove. Okay, so you are, somebody has given you a set, an instance of the set cover problem, and a parameter R. You can produce a for a graph GS, okay, and a C, such that you say that, oh, okay, the set cover problem S has a clique of size R, at most R, if and only if this G of S has a clique of size C, at least C. Okay, so this is a theorem, I can say. Now, how to prove this theorem? Okay, that, so these are called very kind of, these are sometimes called the gadget construction. Okay, and I have to, I don't remember it very on top of my head. Particularly, see, this gadget construction is kind of a bit tricky. Some many can be very tricky. Okay, so right. The another one reason for particularly this gadget construction becoming tricky is that, see, this is a minimization problem, and this is a maximization problem, right? So you are reducing a maximization problem to a minimization problem, and so on. Okay, so if you can do such a thing, then this just says, so okay, this theorem, okay, this theorem, maybe I should write it here. So this theorem, what does this theorem say? This theorem basically says that give me an instance of S, I can reduce it to an instance of click, such that you solve the click problem and we are done. So this gives this statement, that the set cover is less than or equal to click. Okay, so this theorem, I'm not going to prove it right now. If you guys are interested, I can take a look at this construction. I don't want to do it on top of my head, but this thing can be done later on. I mean, we can do it later on, but you can for now take it as a theorem. So this construction is something that we have to think about it, and we have to do it. So these are very creative constructions that people do, and that they are not easy most of the time. not easy to come up with other constraint. Okay, so this is one thing. The other thing is the next one, right? The click is less than or equal to set cover. So what do you do that? Why doesn't this theorem prove this? Right? So this theorem says that for all s, maybe I should write it here in a different color. So this is for all s, right? Give me any instances, I can produce g of s. Now you should do the opposite direction. That for any instance, so the other theorem that would be required would be, and that is also a theorem, that given a g and say c, okay, we can construct s, okay, say s1 to s some, so s is some sets, right, s of a subset, but this s is of course a function of this function of g, okay, it can also be a function of c for that matter, right, and r, which is a function of again s and c, such that, so this is a collection of sets, okay, collection of sets such that here the opposite, right, g has a clique of size more than equal to k, sorry, not k, more than equal to c, if and only if SGC has a set cover of size less than or equal to R. Okay, so if you can, if this theorem, so both of them are theorems, both of them are reductions. These are called the reductions. Okay, and in the 70s and 80s, this kind of work was the most popular kind of work. Even in the 90s, when you reduce one problem to the another, and they're very tricky constructions that people come up with. And if you do this first one, you get this first thing. If you do the second one, you get this one. Okay. So what ends up saying is that, okay, both of them are in from the point of view of complexity, at least from the point of view of polynomial time complexity, both of them are equally hard. Okay, with these two things. And in fact, what will happen is that you can prove that one of them is a NP hard or NP complete problem, and therefore both of them becomes NP complete problem. Okay. So is this clear? I mean, I have not proved this theorem. Okay, I have not gone to reductions. If you guys are interested in the reduction, I can go over the reductions and all. But again, I mean, I would say that for this course, and don't think too much about this non-trivial reductions. The reduction is the very big area that is there. You have seen a slight in reductions, a very simple reductions, reducing clique or vertex cover to ILP, but not the, yeah, tell me.
These reduction, I think this would be easier. Like we can reduce set cover problem easily to the vertex cover problem. Then we can solve that vertex cover and clique just on the complement of that complete graph. Vertex cover and clique problem. That we can do, I think.
So okay, so you are saying this following thing. So you are saying that set cover you will reduce to vertex cover. Vertex cover you will reduce to independent set, and independent set will reduce to clique. Okay, most probably this is something you can do. Okay, so independent set to clique is basically, I mean, given a G, you just look at the G complement, right? That is fine. Vertex cover to independent set is
No, I am saying directly from vertex cover to click. Like a graph G, we will just take that complement of that graph,
Yeah, which that
like
is
in a
exactly
complete
independent.
graph.
That is entirely independent set, right?
Yeah, yeah.
I mean, that is the independent set of this that graph, original graph, right?
Like, I don't know that it is construction, so I think in this way you can do that.
Yeah, possibly. I mean, yeah, possibly you can do that. Okay, so this is just possible that this is, yeah, this kind of a. So you can come up with this kind of huge set of reductions and one after another produce. So this is like you can think of this one just as inequality. Okay, is all this equation. Also, this is written with a p kind of stuff here, but forget that p. Yeah. So this basically means that you are polynomial reducible. You can polynomially reduce set cover to vertex cover. But what I'm not sure is that okay, this vertex cover that is being told right here, this formulation, okay, this is not the what I wrote initially was a easy reduction to vertex cover. This is more of the knapsack kind of stuff, I think. So we have to see whether this set cover goes to this vertex cover. But yeah, but basic idea is same. I mean, you can do some things, and maybe you have to do some kind of a clever reduction here and there. Okay, so is it clear? Did I answer the question that was asked initially?
Yes, sir. Sir, I actually the construction is not needed for this course, so it is okay after this.
Yeah, I will not be asking construction for your. Yeah, I will not be asking construction for your in your NSEM or something. But at least not the more complicated constructions. Okay, this reason is exactly that these constructions can be a there's a lot of kind of gadget stuffs and all that are there, and I didn't want to push it down your throat too much. So the more important thing to know is that there are this concept of reduction. There is a concept of you can reduce one problem to another, and there is a concept of NP completeness, which basically means that it is the hardest problem in a class. Okay, and they are all mathematically sound reductions, proofs, and all. So these concepts are the most important. Okay, and how to reduce it? The main idea is that you have to come up with some clever construction to reduce one problem to another problem. So how to prove? So if I give you a problem P and I ask you prove P is NP complete, how will you do it? You go and there's the huge compendium of or list of NP complete problems. Okay, find so the steps are usually this one. Okay, this is nothing to do with this code, but I'm just saying it. Find the NP complete problem L. Okay, now not just see again technically and design a reduction P to L. Well, this is basically the idea. Sorry, I went the wrong direction. L to P. Okay, so if you design a reduction from L to P, it will mean that P is harder than L. So and since L is also NP complete problem, then it is NP complete. And of course, the third one is that proof that P is in NP. The crucial part for things is that see you can choose any L. Technically, any L should be you should be able to do this. But for some L's, it might be easier to do. And this is exactly what your main idea is to find the correct L for which you can do this reduction. And once you can do this reduction, you prove the NP complete problem. Now, yeah. Yeah, so there are lots of things. If you guys are interested, I can talk about it, maybe not today. So, Yeah, so there are these areas of research after this. Okay, maybe uh, let me get these questions from you, and then I will go into this. Some other questions. So, any other questions that you have? Anybody? So, the last time somebody asked a question that Chandrima told me that if I have to prove things like this, 1 second, I just have to. I hope that is being recorded, right? Yeah. Yeah. So, say I have to prove that L. So, how do you prove that L is in NP? To prove L is in NP. Okay, what happens if I say that I take a L complement and prove it is in NP? Is this sufficient, or is it? Yes, tell me.
It's not like that was my doubt last class.
Yeah. So let me explain. So this is a very tricky thing. Okay, it is sufficient to prove L complement is in NP. Now this is actually very interesting. So let's just quickly revisit the definition of NP. What is the NP? Okay, so we say that say L is in NP if, now very crucially see, okay, if for all x in L, right, there exists right kind of a, we told it as a certificate or a proof, right? I don't know, pi psi of x, so this can be a proof such that, okay, so there exists an algorithm A, polytime, such that A on x yeah, so such that so sorry, what am I saying? I missed it. Such that sorry, I made a okay, such that A on x phi of x accepts, okay, and for all x not in L, right, for all phi of x, A of x comma phi of x rejects. So note that what is happening here. Okay, what is happening here? See, you are giving a proof, right? You are giving a proof. What is the proof? The proof is only for the case of x is in L. Okay, so that means if x is in L, you have to give me a proof that is in L. But if x is not in L, you are not giving me a proof. It says, okay, I mean, for no, for nothing, we will not be able to accept it. Okay, we will not accept, that's all. Such kind of stuff, right? And this is actually the main thing. So if x is not in L, nobody asks for giving a proof. Now, but think of L complement. What is L complement in NP means? L complement means that it is same, there is an algorithm and all those kind of stuff, but then for all x not in L, there exists a phi of x such that A x comma phi of x accepts, meaning you have to give me a proof when something is not there. Okay, and for, of course, the other one is there, that I cannot fool you, right? For all the x in L and for all phi of x, a of x comma one rejects. Okay, so let me give you an example. Okay, so an example is a very useful thing here. Consider this problem primes. What is primes? So primes is the set of all n such that n is a prime. Now we are thinking of this primes as in a binary representation, say. Okay, so 0 1 to the n. Say, I mean, you can think of it in the decimal representation also. No big deal. Now, what is the complement? What is primes complement? Can you say? Somebody say. Hello.
Composites union 1.
Right. Yeah. So it is all the n such that n is a composite number, right? It may be or 1. Okay, so that's all, or 1 is not a big deal. That's there. Now, which of them can you prove to be in, say, NP? Which of them can?
Second one.
The second one can be in NP, right? Why? So by the this is called, this is also called a fact or factorial. Yeah.
We can easily give number
okay.
which is divisor of it.
So what is your certificate?
A divisor.
Right. So the factorial is a divisor, right? Okay. So that means that if I give you an n, the psi of n is basically a divisor of n. Okay, a prime factor of n, say, let's say, or you can even do a even further, a prime divisor of n. Doesn't matter what. Okay, and now all you have to do is that to check it, the algorithm A will have to take this one phi of n, and we'll say that okay, it is accept if phi of n divides n and rejects otherwise. Now note that this algorithm will certainly not be able to, I mean, it will not accept any prime number. Of course, I'm assuming here that that phi of n is bigger than 1 and less than n. Okay. I mean, if you want accept if this one and phi of n is strictly bigger less than 1 and strictly less than n, something like that, right? So it will, whatever you do, if n is a prime number and you try to give it any phi of n, the algorithm will not accept. But okay, I have not yet been convinced that that algorithm that is not a factorization or something. But if it is if it is a factorizable, then of course someone can give me the prime, one of the prime divisor, and I will check it, right? So this means that this fact or primes factor is in NP, or some, or which basically means the fact is in NP, factorial in NP. Okay, fine. So where is primes? How do you prove primes? Right? So primes therefore are in the set in which is the complement of NP. Okay. Okay. So it is usually defined as so there is something called NP and there is something called a co-NP. Now co-NP is a class that if L is in NP, then L bar is in co-NP. Okay, and I don't want to go too much into these details, but what you can see is this following. Okay, there is NP, this is co-NP, there is a P which sits within both of them, and then there are some problems which are in the intersection. And it is believed that the NP complete problem sits here, and that's it. Okay. So what you have proved is that you have proved that primes, fact, opposite of primes is NP. That means primes is in co-NP. Okay. Now this is this doesn't mean that. So for example, take any problem, say vertex cover. Okay. Now vertex cover is NP complete. Okay. You can, I mean, is vertex cover, it doesn't mean, it might be that vertex cover is in NP complete and in co-NP. Is vertex cover in co-NP, or in other words, is vertex cover complement in NP? Okay, that is a hard problem to argue, and we don't know. This is like, if you can solve this question, then you solve almost something very almost similar to P not equal to NP kind of question. Okay, a P equals to NP. So in short, just by proving some of complement is in NP, you are not being able to prove, or you cannot show that that problem is in NP, because complement in NP basically means that it has to be the opposite or something like that. So note that there's one thing that has happened. So it's not for there, or it should also be for there exist. Yeah. Okay. So note that this expression and this expression has one change, right? It has flipped itself. I mean, because of this stuff. So usually NP is considered to be, so NP is considered the there exist class, meaning there exists, X is in L if there exists something. So another way of defining NP, so L is in NP. Another way is that X is in L if and only if there exists psi of X such that A of X psi of X equals to 1. Okay, and L complement, or L complement is in NP, or which basically same as saying that L is in co-NP, where you can say that X is in L if and only if for all phi of X, A X phi of X equals to 0 or 1, doesn't matter. So the NP class is determined by this there exist. So that means there exists a way of proving correctness. Okay, and it is this. Now, okay, so what we have till now, we have that primes is in co-NP. Okay, this is because primes complement is in NP. Now, what if I try to prove primes is in NP? Can I try to prove primes is in NP? Or can I try to prove primes is in NP? What would it mean actually? Primes is in NP means
composites is in co-NP.
That is one way of saying it, but indirectly, if you think of it, meaning I will give you yes, yes, certificate of what?
That can prove if a number is prime.
That can prove a number is prime. So I give you a number, and you have to prove to me that number is prime using that certificate about the witness or something like that, right? So one way of thinking of it is through this usual standard factorization. That means I say that, oh, how can you prove that a number n is prime? Okay, if for all numbers less than n, it is not divisible. Very good, but that's for all. Can I have a there exists kind of stuff? Okay, so a certificate of primes. Now you guys are all, so have you have done some courses in number theory, elementary number theory, in your high school, in your whatever?
So you were taught many of the results in abstract algebra, but not a specialized course in number theory.
No, you don't need. I mean, don't need that kind of number theory. You know, Fermat's little theorem and all those kind of stuff like that.
Yes.
I mean, some again very simple things, right? Like if, I mean, yeah. So I will use some very basic facts to kind of now try to prove primes is in NP. Now this is interesting. Okay, I will prove it actually to you. The primes is in NP. I will not prove you by proving that there exists no factorization of that number, but I'll prove it through some another way. And this is where the beauty of this whole stuff comes, that there can be a lot of other numbers. So say if a friend comes up and says that here is the number n, is n prime? How will you go about it? How will you try to prove it? I kind of talked about it last class, right? That okay, so one thing that you can first check is that what happens if I take for all a to the power n minus 1 is congruent to 1 mod a, not a, n, right? So you guys all know this relation result.
So n has to be.
N should not divide in.
Oh, n is prime.
N should not divide.
A.
N should not divide a. Good. I mean, this is always the case. I mean, I think okay for this. Okay. So, but okay. So let's see this way. Let's write it in a slightly different way. If n is prime,
we can multiply both sides to make it identity for all n.
Yes. If a is prime, then there exists an a such that this holds, right?
Yes, sir.
Yes, sir.
Now, is this an if and only if condition?
No, sir.
No, sir.
Okay. What is an if and only condition? You know this cyclic group this way. So I said take an a which is this in the co-prime to n and all those kind of stuff like that. Not co-prime, it's like, yeah, is a huh?
We'll need this condition for all a from 1 to n minus 1.
Okay. Okay, good. So you're saying for all a from 1 to n minus 1, okay? Good. For all a between 1 to n minus 1. So you are saying that, okay, so I told you there exists. You are saying that, okay, now I want to say that n is a prime if and only if for all a between 1 to n minus 1, a to the power n minus 1 is congruent to 1 mod n. This is what you're saying, right?
So inclusive.
Right, of course. Yeah. Everybody with me?
Sir, I don't know how the reverse inclusion is true.
Okay, so so for any number, okay, what is the minimum thing for which it can be true? If I give you any number n and the a which is say co-prime and all, so there is this thing of this stuff, right?
Yes, sir.
And this
if
is
A and N are co-prime.
If a and n are co-prime, and this is if and only if, right? not if and only. So this is the minimum thing for which this comes
Yes, sir. Yes, sir. Yes, sir.
for true, right?
Yes, sir.
This is the minimum thing for it's true, right? Good. So there are two.
Okay.
So phi of n is the minimum number such that, okay, for all a co-prime and all those kind of stuff, this is true.
Okay, sir.
Okay.
Hmm.
Now, if n is a prime, then phi of n is n minus 1.
Yes, sir. Okay.
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 Now, if n is a prime, okay, this is actually right, not, I mean, this is true, okay, but what you can say something more actually here. So from this you can get this stuff. The issue here is that for all a is there. Do we need it for all a? As we know that if n is a prime, we know anything is of this structure, right? So what happens if I prove to you that's okay? This is something I can say. If n is a prime, if and only if there exists an a, okay, and less than n minus 1, such that a to the power n minus 1 is congruent to 1 mod n, and for all k, okay, less than n minus 1, a to the power strictly less than n minus 1, a to the power k is not congruent to 1 mod n. So this will, what will this prove? If I can prove this statement, what will this prove?
Phi n is n minus 1.
This will prove that phi n is n minus 1. If phi n was something less than n minus 1, right, then there will be some a, I mean, there will be something for which, I mean, for all n, for all a, at phi n it will have been 1. But this is saying that there exists a for which you will not get 1 for any k less than 1, minus 1. I mean, are you guys comfortable with this thing?
Yes, sir.
Yeah,
Yes,
if you're not comfortable, it's like simple, it's a very elementary number theory that we are doing. You can check it out and all, but I mean, if not, just believe me that this is exactly what you can do. Now for this thing, now can you think of a proof of primes? Now can you think of proof of primes? So if you have to convince your friend that n is a prime, how will you prove it?
The certificate will be a.
Okay, and then what will your friend do?
We'll check that these two conditions are satisfied.
Okay, can you check it in polynomial time?
Sir, is multiplication considered a constant operation for this?
Yeah. So multiplication is a constant operation.
Then we can check it in linear time.
What linear in what?
Oh, okay, that's a problem.
Aha.
Linear number n.
Linear in n. Okay, so I can help you. Okay, if your friend comes up and gives you an a, or you give your friend a friend can compute a to the power n minus 1 in a very quick time. Why? It's kind of, how do you produce a to the power n minus 1? So what is it? So let me write down n minus 1 in binary representation. Okay, so this is a 1 0 1 1 0. Okay, so what does this term means? Right, so this term means that at the, this is actually 2 to the power
19.
No, I don't want that last number. I don't want it. I want to really look at this last thing. So this number is what? Okay, so this is, I can say, so 19, right? Okay, fine, good. So if it is 16 plus 19, how can this be 19?
It's 22, sir.
It's 22.
It's 22, right? Okay, it is 16 plus 4 plus 2 is this number, right? 4
Yes.
meaning 2 to the power 4, right? 2, 4, 8, 16, yeah. Plus 2 square plus 1. Now, what any person can do is that you can take A, then you can multiply with itself to get a square. From that, I can get a to the power 4. From that, I can get a to the power 8, and so on. So, I can get a to the power 2 to the power I in how many steps?
I step.
In I steps, right? So, I can produce 2 to the power 4 in 2 steps, right?
Yes.
Similarly, I can produce 4 or 2 square in just 1 step, and so on, right? So since I can produce in a to the power I in to the power I steps, so if you write a particular, say, n minus 1 as summation of j 2 to the power j, right? Not j, whatever, something like some 2 to the power j, where j is in some subset, either some subset of this thing, right? Then a to the power n minus 1 can be written as what? A to the power, the product of a to the power 2 to the power j, where j is in some set, right?
Yes, sir.
Which is nothing but now the number of terms required, this any one of them can be done in j steps. So basically the total number of steps therefore is, right? Now, okay, j steps for this one, for each of them I can do this j steps, and then all I need to do multiply, right? Which is another some log n number of steps, right? So the finally I will multiply all of them.
Sum of S,
Sorry. It will not be sum of s.
it will be sum of S
No.
plus size of S.
So okay, so for each of these terms, so how many? What is size of s? First of all, let's see what is size of s. Size of s is the bit length, right? So this is log n, correct?
Yes.
Size of s is less than log n. So I will do is that I will produce all these 2 to the power I things. Okay, let me see how much time does it take to produce all the 2 to the power I. It is summation over j, right? This is the total number of times takes for 2 to the power j. And then once I produce all of them, then I need to multiply all of them, and that is just size of. Oh, is that what you're saying?
So, in that initial term is log square n, that is fine.
Yes.
The second term, since we need to check for all k less than n minus 1.
No, I'll come to that. I mean, you mean this thing, right? Good. Yeah, I'll come to that. Okay. So now this one, therefore, is basically nothing but log n, order of log n square. Hello, can you hear me? Hello?
Yes, sir.
Yeah.
Yes, sir. Yes.
Okay. So that means that in order log n square, you can produce any power, and checking this thing therefore can be done in order log n square steps, which is polynomial. That's all that matters. Okay, I don't care about order log n or order log n square. It is polynomial in the input size, which is log n. Great. Any question about that? So you are given a, your friend can produce a to the power n minus 1. Check is a to the power n minus 1 congruent to 1 mod n or not in polynomial time? Correct. This is all that I have done here, is just to say that a to the power n minus 1 can be done in polynomial time. Is there any question here?
Okay, sir.
Fine. But what about the next one? What about the next one? How will you check for all k? Can you think of something nice here?
So technically, we don't need to check for all k. We only need to check for factors of n minus 1.
That's very good.
But
That
like
is
factorization is empty, so I'm not sure.
okay. We'll come to that. We'll come to that. Factorization is what, Baba?
Factorization is not a p problem, right?
Okay, but okay, good. Factorization is not a p problem. So what your friend is saying is that, okay, I mean, if there exists a k, okay, this is something next, right? So say a to the power n minus 1 is congruent to 1 mod n. Okay. Now, if there exists a k strictly less than n minus 1 such that a to the power k is congruent to 1 mod n, what does it mean? You can basically prove it immediately that there exists a L such that L divides n minus 1 and a to the power L is congruent to 1 mod n. Okay, fine. Now, so all that I need is therefore factors of n minus 1. All that I need is factors of n minus 1. Of course, your friend is polynomial time restricted. Your friend, your is polynomial time restricted. What does it mean? It means that he cannot factorize n minus 1. But what he can do is that you are the person who is helping your friend. Your friend is unable to. Friend is polynomial time restricted. You have given the a. What can you give? To help your friend, find such an L. What do? You provide
The certificate.
a factorization of L. Of n minus 1, or you provide the L, or basically, okay. Oh, now by the way, sorry, I made a mistake here. I completely made a mistake, and this is where maybe you guys are already. So you can show that for all L such that this happens, this happens. Okay, you need no. It's not like there exists an L. Okay, you have to prove that there is. Yeah, sorry. So there exists an L. So sorry, this is right. It's skipped a step. Sorry, this is right. So okay, so forget this thing. Okay, so to prove that a to the power k is not congruent to 1 mod n for all k less than n minus 1, it is enough to check that for all say p such that p divides n minus 1, okay, or for all prime p divides n minus 1, a to the power n minus 1 by p is not congruent to 1 mod n. sorry, I made a big jump here. So this statement is right. Okay. So if there exists a k, then I know that there will be an L such that L divides n minus 1 that congruent to 1 mod n. But that means that if I have to prove that no such k exists, I have to kind of prove that for every number that divides n, okay, a to the power that number is not congruent to 1 mod n. And this can be done by looking at all the prime factorizations of n, right? So to help your friend, what you can do is that you can provide the prime factorization of n minus 1, right? So what happens to the witness? So the witness is therefore a witness or certificate for primes is what? One is an A. Okay, so this will be used to such that a to the power n minus 1 is congruent to 1 mod n, and we will use the a to the power k is not congruent to 1 mod n for all k strictly less than n minus 1, right? Now to check this thing, you also provide the prime factorization of n minus 1. So this is the prime factorization of n minus 1 is p1 to p term t such that p1 alpha 1 to p2 alpha 2 to pt alpha t is equals to n minus 1. And with that, what do you check? You check that a to the power n minus 1 by pi is not congruent to 1 mod n. Okay. Now you might say, oh, now we have to go for all possible primes. Yes, we have to go for all possible primes future factorization of n minus 1.
So why would we just certificate a polynomial sized?
Good. Why would it certificate polynomial size? So this is polynomial size, right? This is size log n.
Which one?
A.
Yeah.
A is the polynomial size one. How many primes are there? How many primes can there be which is a factor of n minus 1? Okay. So I claim that, okay, the number of, okay, so this is something one thing, okay, you can go and prove this one. These are all simple comparable theory. Claim t is less than log n. You cannot have more than log n prime divisors of n minus 1. Okay, and for all alpha, so all alpha are less than n log n. Okay, none of the powers or exponents can be less than log n, more than log n. This is obvious because primes are all bigger than 2, right? So if there are more than log n primes, then 2 to the power log n becomes more than n minus 1. How can therefore it be equal to n minus 1? Right? And similarly, if every primes is bigger than 2, so if alpha cannot be more than log n, because 2 to the power log n is n, right? So we can, so from this one, what do I getting? We are getting that what is the prime factorization? Prime factorization nothing but p1 alpha 1 kind of stuff, like I am giving you this pairs, right? The total size is the log n of them of size log n each, so again it is log square n.
It will be a polynomial.
Which will be a polynomial. So the size of the witness is now therefore polynomial. Okay. So your witness has increased, but witness is there to help you out and all. Okay. Now is this
kind of clear?
Kind of clear? Okay.
Means I can't understand why t is less than equal to.
Oh, why is t less than equal to log n? So see, this is true, right? Fine.
Yes.
What does it mean? What does it mean? So this means that P1 to Pt is less than or equal to n minus 1.
Yes, sir.
See, alphas are all non-zero.
Hmm.
Alphas are all non-zero. And zero things I am not giving you, right? Prime factorization, you don't give all the primes that doesn't divide it, right? So alphas are all
Yes.
strictly greater than 1. Not strictly greater than or equal to 1, right? So this is the case. What does it mean? See, each of them are bigger than 2. Pi's are bigger than or equal to 2. That's like obvious, so they are prime. So P1 to Pt is bigger than 2 to the power t.
Oh, I get it.
Right? Yeah. Is it clear?
Yes, sir.
Okay, I am not done with this. It should not be clear. There is one place that I have not told you. Can somebody say what I have not told you? You gave your friend A, you gave your friend the prime factorization, the friend. See, you can be a cheater, by the way, right? Remember that. It's the idea that if you want to convince your friend, you can give something nice. But you can give some you might want to basically give some stupid things kind of and try to convince your friend that an n is a prime, but when it is not a prime. You gave your friend A, you gave your friend a prime factorization, and he used it to check something. Why is it that you could have lied?
The factorization.
How?
Like we are just returning pi, we are not returning alpha I.
No, you can return alpha is also. That's fine. You can give pi then alpha I, then your friend can go and check that actually it is this product of pi to the power alpha I into pt to the power alpha t is n minus 1. So when I meant prime factorization, I meant this.
We need to ensure that pi are primes again.
Exactly. How do you know pi is a prime? Okay. So we started from proving pi is a prime, or some number is a prime, and we landed up again the same thing. Your friend cannot accept, understand, I mean, cannot have a proof that pi is a prime. Okay. The only thing left to check, left to verify is whether pi's are prime. Now I am going to stop here at this point, but basic idea is that we started from n, we made something which is a much smaller pi, right? See, each pi must be small. It must have gone down by a factor of 2 at least, right? So you can recursively do it. So now the actual witness should not only come with this one. So the witness should be basically this. Okay, so let me write down finally the final witness that will be there. It will be this A. Okay, it will be the P1 alpha 1 till Pt alpha t such that pi product of pi to the power alpha I equals to n minus 1. And so there are 3 parts to this witness. Witness that pi's are primes. Okay. So to give, now the pi's are already have gone smaller. Okay, and if you do these calculations correctly, you'll see that there is a recursive chain that is happening. And finally, the total witness size will be polynomial in n, in log n. Okay, so I can give you a kind of a write-up that is there, very nice write-up. I will post it in the internet and in the web page. You can go over it and how to complete the proof. But with all this hard work, you can end up proving primes is in NP. And we had already known that primes was in co-NP. So from that, we know that primes is in NP intersection co-NP. So you see that proving something is in NP is much harder than what sometimes it comes up to be. Okay, it's much more fun actually. It's like, I mean, try to convince someone of something. Okay, so I mean, right. So this will show you that primes is in NP intersection co-NP. Now, in the next course, again, if you guys are interested and if it happens and all those things, you can prove this. I mean, you can extend this one. And this is the paper of Agarwal, Kyle, Saxena, that primes is in P. Now, this is a much more involved problem with a lot of more number theory involved in that. But actually, it is presentable in less than a class. I don't want to go into it at all, but yeah. So yeah. So note that. So therefore, we have. So this is how you can prove something is in NP, and that is exactly what I wanted to talk about. Is it clear?
Yes, sir.
Okay. Okay. So I don't want to go too far. So do you have any questions again? I mean, I can take some questions now. And can you please in general, so I will think of this class to be the last class officially. Okay. So there will be no class on Saturday because I don't have anything else to teach. Okay. The rest of it will purely be discussions on problems and all. There is one class I can take for people who are interested a little bit, something that I wanted to cover but I could not cover, and it is not a part of this course as such, that basically says that how to handle NP complete problems. Okay, now this is something that I mean will be the kind of the starting point of, you can say, the advanced algorithms course basically. Okay, this is something that I have not done. If you guys want to discuss this one, I can have a class and discuss it and at least give you an introduction to this whole stuff. And it kind of goes into a lot of other areas like, say, the approximation algorithms, randomized algorithms, and so on and so forth. There's a huge area that is there. Okay. In fact, almost everything that you get in real life issue incidents, they are all related to NP complete problems. So the whole job is basically to come up with very clever ideas to handle NP complete problems. Okay. So this is one thing that I have not yet done. The other thing that I remember doing it is this FFT algorithm. This is not a part of your course. I will not be doing it, but since I promised you, I will upload a video on that. You guys feel free to listen to it whenever you want. Okay, it will not be a part of this course. So it will be more like, I mean, this will be very algebraic. Okay, so that is the reason I don't want to go into this much too much. That about yeah. So this has a lot of algebraic structures to it. So this also I mean, if you are interested, I'm sure this algorithm primes is in P. Okay, so these are the kind of problems that are addressed in the next course, in the advanced computing course, advanced algorithms course. Okay, so these are basically the high kind of yeah. So
what do you mean by handle NP complete?
So see, I have a problem. I have a graph. I want to compute the click number of that graph. you cannot just say that, oh, it is NP complete, I cannot solve it. That is not an acceptable answer, right?
Like
In
how to
real life, you have
actually
to solve it. How do you answer that, right? But I have an ILP. I want a solution. I want to optimize it, right? I mean, I mean, the finance market is basically an ILP, whether to invest or not invest, and so on and so forth, and all. And how much money can I get in there? I cannot just say, oh, this is NP complete, so I cannot come up with a very clever algorithm. That is not a question, right? And exponential time algorithms are not useful. So, what is it that we can do? The problems are possibly not in P. It is NP complete, it is hard, but that doesn't mean that we can throw up our hand and say that that's it, done, right? So,
yes.
I mean, there are various ways. Okay, fine, I might not be able to exactly compute the optimization, the correct optimization, but can I come close to the correct optimization? Can I give an approximate value of the optimization? Can I give a randomized value of the optimization? I mean, randomly and on expectation get the right value of the expectation. Is all of the problems that we are trying to handle, are they, see, I mean, everything is NP complete or something like that is based on worst case time analysis, right? That means there exists an instance which is very hard, but maybe the instances that we are trying to handle are not very hard. Can we kind of understand what kind of instances are easy, what kind of instances are hard? For those instances, can we handle that? And that can be done in 2 or 3 different ways. One is called structurally, like you say that, oh, see, I cannot compute vortex cover in graphs in general, but I can solve vortex cover in planar graphs or such kind of a spatial restricted versions. That is one thing you can do. Or the other thing is that, okay, fine, there is a parameter. If the graph has some particular parameter, as long as that parameter is not too much, I will be able to handle it. Now, what kind of parameter? It can be something like number of edges is the parameter, of course, but you can have parameters like the largest cycle or something called a tree width and so on. So this leads to the subject for called parameterized algorithms, where you restrict your, I mean, the space on which you are trying to solve it, you kind of work on that. Then there are the other issue, other things which are much more complicated and where theoretical understanding of algorithms kind of is at the, I mean, it's like at the edge of that. Means we don't have it. Like many times the ILP problems, okay, that we get in real life, there are very clever, what we call as heuristic algorithms. Now, what is heuristic algorithms? Heuristic algorithms are like, heuristic algorithms are things like we could do something without any reason why you are doing it. Okay, I mean, okay, I mean, do some kind of weird things there. But somehow, in real life instances, those kind of weird things help. Okay, and many of these great works that are going on now are in that area. So machine learning, by the way, is a big chunk of that. We have not a much understanding of what goes on in the real, in this theoretical aspect, but somehow it seems to work. So one of the big thing is called the SAT solvers. Maybe I had told you earlier. So satisfiability is a big NP complete problem, or similarly ILP or ILP solver. Meaning I don't know how to solve ILP. I know ILP is NP complete. Okay, but now there are problems that comes up in real life. Like in real life problems, can I solve them? And so turns out that yeah, real life problems, you apply some kind of ILP algorithm, some nice clever algorithms, heuristic algorithms. I cannot give you any reason why it will work, but it works. It gives you the right answer almost. I mean, it gives you the right answer every time almost, and it's pretty fast. So these are the kind of the other extreme where the, I mean, theory has still not been able to understand what is going on. What is the class of problems for which it is, or what is the class of examples or instances where the algorithm is correctly working, where it is failing and all? It's not very clear. We know that in the worst case, those algorithms are also very bad. and somehow the real life problems seems to be handleable. Okay. And now with this, since now you have ILP solver or SAT solvers, okay, then the comes that, oh, okay, these are NP complete problems. So we have very good result algorithms for handling them. Does it mean that we will be able to solve vertex cover now? Yeah, that's the catch there. There's a lot of things that has to be worked out there. Because when you do the reduction, you lose certain amount of size blow up happens. Even if it is polynomial size blow up, but still it is a blow up, which becomes too much for the practical problems to handle. So all of these things are basically how you handle NP complete problems. Okay, you pick your favorite NP complete problem and try to solve it. Okay, and that is basically the almost whole of algorithms are based on that. I mean, this was a very quick 5 minutes course on a lot of things. I mean, is it anywhere clear? Anything got? Did you understand anything here?
I think so.
Okay. Yeah, it was.
As much as I would want a class on handling NP,
Yeah.
the problem is next week we have to submit about 4 or 5 assignments.
Yeah, yeah.
So I think I will be able to make time, but I don't know if anyone else.
I mean, you can let me know. Okay, even if it is in after the course happens, after the end sem or something, you want to hear a kind of a talk kind of stuff of how to handle NP complete problems and all. I will be happy to do it. Okay, as I told you, this is not part of the course. This is basically kind of what is there beyond this course, what has gone. Okay.
We actually have one assignment after NSEM as well.
Oh, is it? Oh, no, whatever. I mean, you can take your time. I mean, it doesn't matter. I mean,
yeah, like I don't think there's any point giving a talk to a single person.
Yeah, that will be a bit of a boring thing, but yeah, I mean, you ask your friends if they are interested in this. If they are interested in this algorithm course as a whole or algorithm subject as a whole, and they want to know about what is there or what is the current status or what else can be done or what to expect in the next course, I will be happy to give a 1 hour lecture anytime. Means it doesn't have to be, I mean, that can be in middle of January also. Okay.
Sir, I am interested if it is after NSEM.
Yeah, whatever. I mean, you guys let me know. So this particular problem, this thing is completely nothing to do with this course. Okay. So in fact, I would say that don't think about this one. It is about more about intention. I mean, interest in algorithms. But before the end sem, I would suggest that if you guys want to have classes, it should be more on maybe problem solving, doubt clearance, and so on. Okay. Okay, so maybe I will stop here now.
Sir.
Yeah, tell me.
Sir, I have a question regarding NSEM total marks. You said that there will be 8 questions.
Yeah, 8 questions, 15 marks each. It has been sent to moderation. Okay, if the moderation committee feels that it is a too much of a work on all, it might be reduced a little bit. Okay, I don't think it is too much of it is too much of it's too hard. Okay, so right now 8 questions, 15 marks. You're supposed to attempt all of them, which is 120 marks. Okay, this is how it is now.
And so how it will be graded down to
40 marks or 50 marks, 50 marks.
Okay.
So is it like a 20 mark buffer or?
Yeah, so that is something. I mean, I have not given a 20 marks buffer right now, but depending on what the moderation committee says, I will take a call on that. I mean, that part is not yet there.
So like, is one question equivalent to one assignment question, like in level of difficulty and writing?
Yeah.
I mean, I couldn't complete any assignment within 3 years, and each assignment only had 6 questions. So
no, many of them will be kind of
I
easy. Yeah, okay. I mean,
Yeah, that's
okay.
why I wanted to know the difficulty level.
Yeah, I mean,
For the last
yeah.
two assignments, I took more than 5-6 hours to solve all the problems. So
Right, I understand that. Okay, let me see. I will possibly water it down to some level. Okay, yeah. Sorry, what did I say? Yeah, I told 8 questions, right? Okay, fine. Yeah, 8 questions, 15 marks. So, some of the questions are not hard at all. Some of them are a bit more involved up there. But okay, I will try to water it down. I mean, anyway, this is in the middle of moderation level. Okay, so there are changes that will happen at this kind of things. But
Like, I think you said there are no repetitions or, easily Googleable questions.
no, that is not there.
Right.
That is
So
not there. Easily
every
Googleable questions are
question,
not there. See, that is
right, and
also,
that makes
but the questions are
that.
not hard.
So that's the problem. A question, if it is easy,
Yeah,
I think it will be Googleable.
no.
I okay. So
I'm sure you can Google it, but I mean, if you Google it, you will spend more time.
that might be an issue. Like,
Yeah, so I would say that I mean, Googling is not the useful thing at all. Okay, so don't I mean, put your eggs in the basket of Googling things. Okay, use it as a kind of a take open book kind of stuff like that. You don't have to remember any particular thing, right? You can have all the stuff that are there. I mean, if you just want to have a quick look at what is the DFS or BFS or Dijkstra's or whatever prims and all, what are the algorithm, what are the pseudocode, what are something that you can do quickly, right? But don't try to, I mean, if you try to find the solutions at that time, I don't think you will be able to do it. Okay, instead of that, trying
So,
to solve it yourself will be much easier.
so say in the exam, if you have to use binary search or DFS, can we just
Yeah,
write
yeah, yeah,
DFS or
yeah, yeah,
binary
yeah, yeah,
search?
yeah, yeah. I will, you don't have to write anything that has been done. Okay, you can just say DFS or you can write the frames. Okay, yeah, yeah. Don't spend too much time on, yeah, it's on the pro algorithm design. Okay, in these things I will not be too worried about, oh, the pseudocode and all those kind of stuff. Okay, you guys know what a pseudocode is, you know how to write it and all through the assignments and all. In this course it is all about design. Okay, so you use any black box there if you want. If you do binary search and find this one, that one line is good enough for me. Okay. Yeah. Okay, I will possibly water it down a bit, maybe at least make it a 10 or 20 marks buffer. But I don't think it'll be too hard. Okay, and the only advice I can have is that don't don't say really think that, oh, it is everything. I mean, there are, by the way, this will be true for any subject. Okay, I can tell you as a secret that since we know that all of them are Googleable and all those things, the question papers will be set in such a way that if you Google or if you, then it is not that you cannot be Googled. Okay, possibly you have to do it, but it will not be straightforward Googling. It will not be a cut paste Google and then find out something and something like that. Okay, so which means that if you spend time in Googling and trying to find out your solutions, you will be ending up spending way more time in that. Okay, I mean, so don't eh, prepare for any class this semester with the hope that I will find the solution by Googling. I mean, prepare it as a normal class. It's a bring your notes to class kind of class. I mean, this is my advice. I mean, this is like a else it will be pretty hard. I can imagine that many of you are thinking that, oh, this year's exams are pretty trivial. I'll Google it and find out and everything done. That will not happen. Okay. Yeah, any other questions?
Sir, what would be your policy for exactly copy the answer from a website?
I mean, I don't know, honestly. I'm not going to search it out or exactly copy the answer from our website. Okay. If you do that, if you find the website and copy it and all, I mean, you'll get full marks. I mean, that's all I can say. Okay. I mean, I can only verify if you two of you have copied from each other or copied. That's true if you have copied ditto from each other. I mean, there's only so much that I'll be able to do. Okay. I mean, yeah, it's an honor code that you have to go for. I don't have any way of finding out whether some problem is copied from the internet or not. And I will. Yeah. How will what?
How elaborate we have to give our proof of correctness?
Not necessarily too much. Okay. So you have done a lot of small parts, right? Like you know,
yeah.
so you can use those proofs directly. I mean, you don't have to write it up.
Well,
I mean, like in
so
this. Yeah.
Like for the things we have done before, I think we won't have to give proof of correctness for that. But
Yeah,
like
but
some
also
problems,
you can use things like, say, as in Prim's algorithm, by this kind of technique this will work, or something like that is a valid argument. Okay. I mean, if you can use all of that as a black box. Okay. You don't have to repeat things. I mean, I am not going to insist that, oh, you have to, I mean, give proofs. I mean, almost in the same level or something like that. I mean, nothing. Yeah, so these proofs and all that was there in the assignments, they were fought so that you know what is the proof, how to write it up, and all of that. In the exam, I would be pretty lenient on it. You have to give me the design, the analysis algorithm, and give me a high level picture of why this is correct, what is the time complexity. Okay. So, yeah, don't try to write none of the problems, this is something I am telling you, okay? None of the problems should be more than 1 page long. If you write it in hand, if you write it in type it up, should not be more than half a page long. Okay, or maybe 5 steps or five points or something like that. Okay, so take that one as a thumb rule and kind of write it up. Okay, any other questions? Okay, so if not, let me stop here. And Anvit, I will depend on you to kind of tell me when you guys want some extra classes and for discussions and so on and so forth. Okay.
Yes, sir.
Yeah. Perfect. Okay. Chalo, see you.
Thank you, sir.